Hey, class, this is Mr. Roberts, and we're going to go through the study team tests that we took last week, just so we can kind of help you figure out if you made some errors, what you could do better, and kind of give you an expectation of what you can look for as you take your individual test moving in this week. So the first problem asks us to examine the graph of f of x at right. So here's this relationship that's graphed for us. And the first question we're asked is, does this appear to be a function? And in this case, I would have to say yes, because here's the thing that's important to me. Each x value has at most one y value. And it doesn't matter what I pick, right? I can arbitrarily just circle, here's an x. Well, let me circle it so I can see that better. Here's an x, here's an x, here's an x, and let's do another one. I'll pick this x. So when I look at each of these x's, right, the thing that I notice is that all of them have at most one y value. None of those x's have more than one y. So if, for example, I give this function the value 5, I can see, well, if I give it 5, it's giving me this answer. What do you mean it's giving me this answer? Well, because this curve is up here at 7, I would say when I give it 5, it's giving me about the number 7, right? So when x is 5, this function says 7. If x is, let's look at this one instead. If x is 3, right, what does this function give me? Well, the function gives me back a value of 9, right? Actually that's at 10. So 3 always gives me 10. 3 gives me 10. Right now, 3 gives me 10. 3 never gives me anything other than 10. So I know that I have a function if each member of the domain has at most one y value. At most one y value. Even this 8 right here, right? 8, it never gives me any value, and that's fine. It doesn't have to give me a value, right? But it gives me at most 1. So the question might be, well, how do I know if I don't have a function? Well, a relationship that's not a function might look something like this, right? It would have to curve back on itself somehow. So if I look at this, right, there's a problem here because when I look at the y value 11, you can see that there's 1, 2, 3 different values, right? If y is 11, it could be giving me 4, it could be giving me 6, or it could be giving me an answer of 9. That's not a function, right? Because a function can have, for each x, it can have at most one y. So that's that first question right here. Does this a relationship appear to be a function? I would say yes, and then it also says explain. So I would say yes, this appears to be a function, and then the explain, I'd say each x value gets at most one y value. You can take that back to the soda machine, right? We went over next door. When I hit Diet Pepsi, right, that is my x value. That's input, button for Diet Pepsi. And when I push that, if it's a functioning machine, I'm always going to expect that I'm going to get the same thing consistently and predictably, right? So when I push that, I get Diet Pepsi. If I was to push that, sometimes I got Diet Pepsi, sometimes I got Mountain Dew, sometimes I got Dr. Pepper. It's not a function because those inputs that I'm giving it are not giving me back a consistent and predictable output. All right, what is the domain of this function? Remember, the domain are all of the x values that make this true. So you can say a lot of different things for this one. If I look at it, I can see my domain are the x values, and I can see that it looks like it starts at 3 and goes all the way up to 6. So for this class, I would be happy if you said the domain is all the x values from 3 to 6. You could just say that. What is it? It's the x's from 3 to 6. The domain are the x values from 3 to 6. And that would be fabulous, right? What's the domain? The domain is all of the x's from 3 to 6. If you give this function 3, it's going to give you something back. If you give this function 5, it's going to give you something back. If you give something outside of that domain, right? If you were to give it like 11, it doesn't have a value it can give you back. But everything in the domain, everything from 3 to 6, it can talk about. The other thing that it asks you is, what's the range of this function? The range are those possible outputs I can get. And if I look at this closely, I could see that the smallest output I can get for this function looks like it's about 2. And it looks like the biggest output I can get, right, way up here, is 10. So I would say that the domain of this function, right? What can I get out of it? I can get everything from 2 up to 10. My domain, I can give it things from 3 to 6. I can give it those. What does it give me? That's the range. It gives me everything from 2 up to 10. So you can see I wrote that down, right? The domain, the domain is the x values, the range are the y values, right? And my y values are everything from 2 all the way up to 10. So the range are the y values from 2 to 10. I can get a 2, I can get a 10, I can get anything in between. I can't get anything bigger than 10, and I can't get an output that's smaller than 2. So again, domain, what can you put into it? Range, what can you get out of the function? The next question on this test says, what is the value of f of 3? So if I'm calling this the relationship f, and I give it 3, right? You can see I put a circle right here. I'm giving it that value from my domain. The question is, what do I get out of it? Well, when 3 goes into this function, it goes way up here, and you can see that it gives me the number 10. So to write that down, I would say the following. I'd say f of 3. When I give it 3, it gives me 10, right? 3 goes in, 10 comes back. 3 goes in, 10 comes back. The next one says, what is the value of f of 6? Okay, so I'm going to give it 6. I'm going to give it the number 6. If I give this function the number 6, what does it give me back? Oh, it looks like it gives me, when I give it 6, when 6 goes in, it looks like it's going to give me back the number 6. So 6 goes in and 6 comes back. So the value of f of 6, I would say that f of 6 is 6. 6 goes in, 6 comes back. And then the last question on this page says, hey, what value of x, and it says values possibly plural, there could be more than one. It says, what values of x will make the function give you back a 7? So this is a different question, right? Before I was saying I was giving it things, right? I was giving it 3, I was giving it the number 3, I was giving it the number 6, and I was asking, what does it give me back? This one says, what can I give the machine? What can I give this function so that I get an answer of 7? So see, I'm asking, it's backwards now. It's saying, hey, if I want to get an answer of 7, right, what do I give it to get an answer of 7? And I can see there's 2 points here. It looks to me like if I give it 2, it will give me a 7. And it also looks like to me, very close to that, if I give it a 5, it will give me a 7. So the 2 values that apparently give me an answer of 7 are 2 and 5, right? If 2 goes in, the function gets up to 7. And when 5 goes in, the function gets up to 7. So that's the first page of our study team. On the second page, we're asked to simplify some monomials here, right? And these are all it's just a collection of factors, and it's asking me to collapse it and make it simpler to read and simpler to evaluate. So the first thing I notice on this problem is that I have some factors of x. I'll underline that with this green. I have some factors of x here and here. And I also, in addition, have some factors of y. So the question is, it's all multiplication, right? Factors are things that I multiply together to get a product. I'm multiplying these factors. How many factors of x am I multiplying? Well, when I look at it, right, I have 5 factors of x, and I have 1 additional factor of x. So the number of x's being multiplied is 6. So I have 6 factors of x. So part of my answer is x to the 6th power, 6 factors of x. And the other part of my answer is that for y, right, I have 3 factors of y right here. And then I have 7 more factors of y right there. So it's y, and then times 7 factors of y. So that's a total of 10 factors of y. So this is my answer for part A, x to the 6th times y to the 10th. The next problem, I'm squaring something, right? So I'm squaring things, I'm squaring a big thing and I'm squaring something inside. If I look just first inside the parentheses, right? If I look just inside the parentheses, the only thing that's getting squared in those parentheses is x is getting squared, right? This exponent of 2, right? This exponent of 2 right here only applies to the x. So inside of the parentheses, there's a 2 and then an x and then an x, right? So let's understand that. But outside the parentheses, if I look at this, right, this says I've got 2 of everything that's inside of here. So I'm going to write that thing twice. So I've got 2 of those, so I'm going to write 2x squared. That's one of the things that was inside the parentheses. And then I have another one, 2x squared. That's the other one. So when I look at that, again, I'm going to say that the squaring here is only on the x. There's no parentheses around the 2x, right? There's no parentheses around the 2x. It's just the x that's getting squared. So what I have here is I've got a 2 times a 2, which is the number 4. And then I've got x squared times x squared, right? If I've got 2 factors of x and I multiply by 2 more factors of x, that's a total of 4 factors of x. So this is 4 times x to the 4th power. So that would be my answer for B. For C, if I look at this in terms of rewriting this, coming up with a giant 1, that 5 is 2, that 10 rather, the 10 in the top, that 10 is 5 times 2. So I know that that's the same thing that I started with. And in my denominator, I've got just this 5. In the top, I can see that there's 12 factors of x. In the bottom, I see there's 7. So I want to break it up to make a giant 1 here. So what I'm going to do is I'm going to write this as times x to the 7th. And in the numerator, I'm going to write x to the 7th times x to the 5th. So if I look at this closely, there's 7 factors of x in the top times 5 factors of x, which is 12 factors of x. So one of the things I want to make sure of was when I write something down, I'm always asking myself, is what I wrote down the same as what I started with? Well, 5 times 2 is 10, and x to the 7th times x to the 5th is x to the 12th. What's nice about this at this point is I can see the giant 1, right? I know that 5 over 5 is equal to 1. They're factors, right? They're things in the top are being multiplied together. So I have a common factor, right, of all these factors of 5. The other thing I have is this 7, x to the 7th over x to the 7th. So when I write that down, the only thing that I see left in this problem is I see a 2 times x to the 5th in the top, right? So if I was going to write down my final result, I've got a 2x to the 5th in the top. And the denominator, right, I've got a giant 1 times another giant 1. So there's just a 1, right? 1 times 1 is 1. Now, I can choose, and I probably would write it like this. I would say, look, because that denominator is just the number 1, I'm going to write this as 2x to the 5th power. This is my answer that I would finish with for that, for part C. Let's look at part D. Part D. There's a 5, right, and there's no common factor. So I'm just going to write this 5. And in the denominator, I'm going to take this x to the 5th. I'm going to break that as an x to the 3rd times an x to the 2nd power. And then on top, I'll write the x to the 2nd power. So I hope you can see why I'm doing that. I want to identify the giant 1. I've got an x squared over x squared. So I can see that when I write it out like this. And this is the giant 1, right? X squared divided by x squared is equal to 1 because they're all factors. So what I have in my numerator, I have a 5. And what do I have in my denominator? I've got an x to the 3rd power. So this is the simplified version of that expression, right? This simplifies to 5 over x cubed. And then finally, the last, oh no, there's 2 more of these. Oh, that's so exciting. There's 2 of them. This next one, I've got factors of a and b, and they're both in the top and the bottom. So if I look at my factors of a in the top, I can see that's a to the 4th power. I'm going to just intuitively decide to break that up as a squared times an a squared. My motivation for that is I can see that I've got an a squared in the denominator, right? So I know, so I know that that's going to give me at least one giant 1, right? A squared times a squared. AA times AA is a to the 4th. So a squared times a squared is a to the 4th. That's what I have in the top. And I have a squared in the bottom. The other thing that I see is in the top, I've got 5 factors of b, and in the denominator, I have 3 factors of b. So I'm going to look at this denominator as b to the 3rd times b to the 2nd. And down below, I've got the b to the 3rd again, right? So in the top, BB is b to the 5th. And then the bottom is BBB. So what's my giant 1? Here we go. This is a squared over a squared is a 1, and b cubed over b cubed is a 1. So I'm left with, in the numerator, what am I left with? I'm left with a squared b squared. And in the denominator, there's just a 1 left. So I'm going to write that as a squared b squared as my final answer. And then finally, let's move to the last problem on this page, this right here. 3AAA BBA. That's a ridiculous way to write that, right? So the question is, how many factors of A do I have? Well, I have 1, 2, 3, 4 factors of A. And how many factors of B do I have? I have 1, 2. So what's my answer going to be? Well, I've got this 3, and there's a 3 out front. And then I said I have 4 factors of A. So there's an A to the 4th, right? That's AA. And I've got B squared. B squared, what's that? That's B times B. So this expression that I've written, right, still preserves that I've got a factor of 3. I clearly have 1, 2, 3, 4 factors of A, and I have 2 factors of B. So this is the simplified form of the expression 3AAA BBA. Let's move on to the next page. So we're asked to solve 4 equations. Remember, solving an equation means finding a value of x that makes this thing true. It makes it true. And I'm going to begin with a property of equality that says, hey, if you have things that are equal and you add the same thing to both sides, you're going to get things that are equal. So I have this equation. Let me make the pen just a little bit thinner. I have this equation. I'm going to rewrite it as 12x equals, that's going to be 24. Now, whenever I write something down like this, I always say to myself, what did I do to both sides? What did I do to the left? What did I do to the right? And I don't write it down because I like to mentally think about it. Well, on the left, I added 7 because I had a 12x minus 7 plus 7. It leaves me with just 12x. On the right, I added 7 also. So on both sides, I added 7, right? Addition, property of equality. If you have equal things, you can add the same thing to both sides. 17 plus 7 is 24. That's where I'm at right now, right? What I had has become this. This is equivalent to 12x equals 24. And the next thing I'm going to do is I'm going to take both sides and divide it by 12. Okay, so if you have equal things and you divide both sides by a value that is not 0, you're going to get equal things. Well, 12x divided by 12 is going to give me x. And on the other side, I've got 24 divided by 12. It turns out 24 divided by 12 simplifies to 2. So x is 2. Is that the solution? Good question. I'm glad you asked it. If I look at my friend, the calculator, right, and I say to it, oh, calculator, here's the number 2. Ba-doop. There it is, right? There's the number 2. I want you to take 12 times that number 2. Why did you do it that way, Mr. Roberts? I don't know. Sometimes it's more complicated, right? But I went up and I grabbed it. 12 times the 2. And I want to subtract 7. Now, I know that this is true if the left and the right-hand side are the same. Well, I can see the right-hand side 17. And I can see that when I placed 2 in there, it made the left-hand side 17 also. So when x is 2, both the left and the right are equal to 17. So that's my solution. Right, let's move on to our next equation. This next equation, same kind of thing here. I am going to, let me write something and then you say, what did Roberts do? What did Roberts do? In 3, 2, 1. He took away x from both sides. Right? I subtracted in value of x from each side, the left and the right. I had 4 x's on the left. 4 of them, take away 1, gave me 3 x's. I had a single x on the right, take it away. You can see it. There's no x's there now. What did Roberts do? Oh, I subtracted 1 from both sides, right? I subtracted a 1 from the left-hand side. I subtracted a 1 from the right-hand side. What did Roberts do? Well, I divided both sides by 3, okay? Dividing the left-hand side by 3, it was 3x. Divided by 3 is just x. And on the other side, negative 6 divided by 3 is negative 6/3, which happens to be negative 2. Now, if I come back over and I show checking that one, let me clear the calculator. Clear. This time, I think my answer is negative 2. I will enter the negative 2. And watch what I do. I'm going to go 4 times, go get your x, got it. Bingo. Plus the number 1. Now you can see when I did that, it made a negative 7 on the left-hand side. So when I plug that in, the left-hand side became the same as negative 7. And on the right-hand side, I'm going to go get the x. There it is. there's the x, gotcha, minus 5. Well, when I put the x into the right-hand side, it also made this side negative 7. So because, right, negative 7 is equal to itself, when x is the number 2, right, the moment that x is the number negative 2, both the left and the right become negative 7. So that value of x is the value that makes this statement true. It makes both sides become negative 7. All right, let's look at this one. Couple of ways we can do this one. I don't really have a preference, and if you do, that's great. Go with your preference. I'm going to start by using, right now I'm going to use what I call the simplest form of this thing I call the distributive property. I'm going to distribute a multiplication problem across an addition problem. If you're interested in how do I know this is true, ask me sometime and I'll show you. But if I do that, I'm going to get 4, and I'm going to multiply that times the 2x, and I'm going to also multiply the 4 times the positive 1. 4 times 2x is 8x, plus 4 times 1 is 4, and that's 20. What did Roberts do? You know what I did. I took away 4 from both sides, right? I subtracted 4 from the left. I subtracted 4 from the right. What did Roberts do? You know what I did. I divided by 8, both sides, both the left and the right. By the way, that's the same as the number 2. So my claim is that when I plug 2 into this equation, it gives me the correct answer. Without using my calculator, I can demonstrate that to myself. 4 times 2 times the 2 of my answer, right? Plus 1. Okay. 2 times 2 is 4 plus 1 is 5. 4 times 5 is 20. Yeah. When I plug 2 in, it makes both sides of that equation the number 20. It is the solution. All right, last problem. For this one, I probably really need to use the simplest form of the distributive property, right? So I am going to go ahead and distribute this 4 to both the x and to this negative 10. So I'm being very mindful of the sign associated with that 10, right? It's not just 10, it's negative 10. So I'm going to rewrite the left-hand side, 12 plus 2x. On the other side, I'm going to have 4x minus the number 40. Okay? What did I just do to both sides of the equation? Answer, I took away 2 x's from both the left and the right. I took away 2 x's. What did I just do to both, what did I do to both sides of that equation? The answer, I added 40 to both sides, right? I added 40 to both sides. Convince yourself of that. Did you? Yeah, he says he added 4. Oh, I added 40 to both sides. What did I just do to both sides? I divided both sides by 2, right? 52 divided by 2 is 26. X is the number 26. Is that the correct value of x? I want a calculator now. Why? I'm insecure, right? I like calculators and I like to get efficient with them. So I think the number is 26. So I'm not going to enter it ahead of time. I'm just going to go 12 plus 2 times 26. Enter. I got a 64 on the left. On the other side, I got 4 open parentheses, 26 minus the number 10. 26 minus 10. I got what? So when x is 26, both the left-hand side and the right-hand side became 64. You can see it on the calculator. It made both sides become the number 64. All right, moving on. Our next question involves 2 functions, right? The 2 functions you're given are f of x and g of x, and we're asked to evaluate those for certain input values. So if I look at A, it says, okay, you're going to give the function f the number 3. So here comes 3, and it's going to land right into the function f. And this is how I show that, right? What is the function f? It's 4 times whatever you're giving it plus 1. See, I just wrote that down. 4 times whatever you're giving it plus 1. I'm giving it 3. So I'm going to put the 3 in there. Where'd that come from? That's the input. That was the input. When I evaluate this, I'll know the output. Well, when I evaluate this, I get on this side, I get 4 times negative 3 is negative 12 plus 1. F of 3 is negative 11. So when I give, what? I didn't give it negative 3. Mr. Roberts, clearly you need to put your glasses on. I don't have them. You're giving it positive 3. Oh, yeah, you're right. I am giving it positive 3. If I give it positive 3, that means I've got 12 plus 1. That means I get 13. So when I give the function f the number 3, here's 3. What's it give me back? It gives me 13. 13 is the output for the input of 3. Okay. This one's right here, so let's just do this C, right? I can see C. It says, what about if you give it 0? Okay. If I give it 0, that says it's 4 times the input. The input is 0 plus 1. Well, 4 times 0 is 0. So when I give the function 1, no, when I give the function 0, it gives me back 1. Here's 0, it gives me 1. So f of 0 is 1. When you give it 0, you get 1. That's how I read that sentence. Okay, the next one, it says g of 2. Really? G of 2. Okay, so g of 2. I'm going to give this function 2. That's what is going to be my x. And then I have to square that. So I like to put extra parentheses around where I'm giving it the value. So I'm giving it 2. That means a 2 is going in for the x, right? So when this function g gets 2, a 2 lands right there. Then this becomes 2 minus 4. Okay. 2 minus 4 is negative 2. So this now becomes negative 2. I'm going to square that. Ooh, I know I can make mistakes with this. No, I can't make mistakes with this. I got this. If I take negative 2, and I square it, it gives me positive 4. I do want to make you aware of something. Like on your calculator, be careful and be intentional. If you were to enter the negative symbol first and then 2 squared, this is the opposite of what 2 squared is. Well, 2 squared is 2 times 2, and the opposite of that would be negative 4. So be aware of this, right? I'm clearly plugging in and I'm squaring negative 2. So be thinking about that so that we're sure that we're getting the correct output. The last one is it asks me is what's f of 4. So I'm back over to this other function f. I'll do this one up above here. It says, hey, if you give this function f the number 4, what's it give you? Well, that's 4 times the input plus 1. 4 times the input is the number 16, and 16 plus 1 is the number 17. So f of 4 is 17. F of 4 is the number 17. You give it 4, you get back 17. All right. Oh, my goodness. It snuck up on me. There's 2 more questions on this page. I'm sorry, class, I'm not leaving. So this one says, what's g of 0 plus f of 2? Ugh. I haven't figured out what f of 2 is. So, okay, so this is a little bit more complicated, but I'm still writing those rules down, and you can see those rules on your paper, right? So the first one says I need to figure out what g of 0 is. So I need g of 0, right? Well, g of 0 is going to be 0 minus 4, and then I'm going to square that. So all I've done is I plugged 0 into the rule for g. You can see, right? What's the rule for g? It's up here. The rule for g is you put in the x, you square that, and then you take away 4. So I plugged in 0 into that rule. And then I need to plug in 2 into the other rule. Well, the other rule is 4x plus 1. So I'm going to say plus, I'm going to add to that. The other rule is 4 times x and then plus 1. Okay, well, this g part is going to become a negative 4, that gets squared, plus 4 times 2 is 8, and then plus 1. Okay, negative 4 times negative 4 is 16, plus 9. Okay, 16 plus 9 should be the number 25. And yeah, I'm not, well, I am. Are you really? Yeah, I am. I'm going to look at it. So 16 plus 9 is the number 25. And 4 4 times 2 plus 1 really is 9. Yeah. And then, oh, I should show it the right way, right? I want to square -4, so it's -4. And then that gets raised to the second. That's going to be an error. That is, I entered that incorrectly. To enter that, this needs to be a negative symbol. And then over here, that needs to be to the second power. So that is 16. All right, last question then on this page is this one. It says, what is f of 10? F of 10. So again, my rule f of x was 4 times the input plus 1, right? 4 times the input plus 1. So my input is 10. So where x was, I'm going to place that value of 10 and add 1. So f of 10 is going to be 40 plus 1. F of 10 is equal to 41. So that's the last answer on that page. All right, let's move to our very final page. I think most of us did pretty good on this. So it says we're going to create a table, graph, and equation to match the tile pattern below. If I consider this tile pattern, when I move from figure 1 to 2, you can see I'm adding this, 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 and this. So it's growing by these 4 tiles. When I move from figure 2 to figure 3, I can see it's growing here, 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 and here. So every single time I move forward, it's just growing at the corner. So if I knew that this was figure 1, and I have a pattern here, 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 and here, what's in the middle there would be figure 0. So I'm asked to draw figure 0, and figure 0 should, can I draw a square? Figure 0 should just be a square right there in the middle like that. So I start figure 0, and you can see I add four tiles above, below, left, and right, add 4 tiles, add 4 tiles. So every single time I'm adding 4 tiles. Now, if I was to turn this observation, this situation into a table, I could say, well, I've got figure 0, I've got figure 1, 2, 3, 4. I'll go to figure 5. Number of tiles in figure 0 is 1 tile. The next one has 1 plus 4 more, right? So this has a total of 5 tiles. So it's got 5 tiles. The next one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 tiles. And then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So every single time I'm adding 4 more tiles, right? To get to the next one, I'm adding 4 tiles. And in fact, I think I can write this equation here, right? It's if y is the number of tiles, that's 4 times whatever x is plus the number 1. So if I was just pick any one of these, like if I say, what about this one right here? Well, 5, figure 5. Well, 4 times 5 is 20, plus 1 is 21. So that works quite nicely. The other thing I'm asked to do is produce a graph. And it's going to be the same numbers in this table right here. So at 0, I'm going to plot the point 1. There it is. At 1, I'm going to plot a point at 5. Okay, at 2, I'm going to go all the way up to 9. At 3, I'm going to jump all the way up to 13, 9, 10, 11. No, 9, 10, 11, 12, 13. And then at 5, I'm going to jump all the way up to, or 4, I'm going to jump to 17, which is actually slightly off this graph, right? So I'll just approximate it. It's here. So this is my pattern, right? You can see those points, and that's exactly what's going on. If I wanted to, for clarity, I could go ahead and extend this pattern by just drawing the line that goes through them. But you know, I actually might not do that because we're talking here about figure numbers and numbers of tiles, and those are typically kind of whole number things. They're not necessarily things that would be parts, right? I can't say figure 1.2, figure 2.68, right? It's figure 0, figure 1, figure 2, figure 3, etc. So that would be the figure. And the final thing is, like, it says how many, if I was to continue this pattern, how many blocks would be in the 8th figure? Well, I don't have to continue the pattern, right? What I'm going to do is I'm just going to say, let's just put the number 8 into this rule, right? 4 times 8 and then plus 1. 4 times 8 is 32. Plus 1 would be 33. So there should be 33 blocks all the way out in the 8th figure. Well, Thanks for spending the whole time with me, right? 34 minutes, 35 minutes. Honestly, if you do this, you go through, you think about this with me, and you listen to my crazy rantings about what input, output, domain range, whatever, I hope you'll do better on the test. I hope you let this kind of sink in. This is Ms. Roberts at exactly 35 minutes and 12 seconds saying goodbye.